Hi, this is Frank, and this is a follow-up video to our previous eigenvalue video. So today we're going to define eigenvectors and two examples of how they're used, given in the previous video. So eigenvectors are a special set of vectors associated with a linear system of equations, for example a matrix equation, that are also sometimes known as characteristic vectors, proper vectors, or latent vectors. Now you may notice that this definition is very similar to the eigenvalue definition, and it's because these two are very closely related. You need eigenvalues to get your eigenvectors. So let's take a look at some examples. Okay, so now we're going to look at the problem from the previous video of finding the eigenvalues of 3, 2, 2, 3. Now, we found them to be 1 and 5, so we're going to use these values to find our eigenvectors. And for the first value of 1 here, lambda is equal to 1, we're going to find the eigenvector relating that. So we start with our original relationship, and we're going to subtract this on both sides. So we're going to get 0 is equal to lambda times r minus the matrix times r. Then we're going to use our identity, r is equal to the unit matrix times r, and you can check if that's true or not, which it is, which then leaves us with 0 is equal to lambda times the unit matrix times r, subtracted from our big matrix times r. Now we could see that there's the vector r on both sides. We can factor that out, which will then leave us with our lambda times the unit matrix subtracted from m multiplied by the vector r. So now, without a more rigorous mathematical proof, being a physicist, we could just assume all that rigor is there and just look for the simple value. So to simplify it, we could just use this equation here. Our lambda is equal to 1. Our unit matrix is going to be 1, 0, 0, 1, subtracted from the original matrix, which, as a reminder, is 3, 2, 2, 3, 3, 2, 2, 3, which then gives us our equation that we can now simplify. So, multiplying this out, we just get our unit matrix, so we don't have to worry about that. Then we go through matrix subtraction here. 1 minus 3 is going to be negative 2. 0 minus 2 is going to be negative 2. 0 minus 2, also negative 2. 1 minus 3 is also going to be negative 2, which then leaves us with a matrix times our column vector. Now that we have our matrix times our column vector, we could make our lives a little bit easier and row reduce. So we have this matrix here, and it's going to delete out the second row, which would give us that matrix times r, and we could row reduce even further and set those equal to 1. So we have 1, 1, 0, 0 times the column vector r. Now, we know that r from before is equal to x, y. So we could rewrite that, just simply plug that in as 1, 1, 0, 0, x, y with our brackets. And multiplying this out, we would get x plus y equals 0, and since that equals 0, and 0x plus 0y equals 0. Now we could ignore this bottom one, because that's 0 equals 0, which is true. What we really want is this top equation here, because that's going to give us our relationship between x and y. So, with that, we could say x is equal to negative y. Now that we have that relationship, we can look back and plug it into our eigenvector form of x, y. And again, we know that x is equal to negative y. We could simply plug x in for that x, which would give us negative y, y. Now, we could also say that y is equal to 1 for simplicity, which would then give us negative 1, 1. And typically we do that just so it's nice and simple, because we just need our directions for this eigenvector. So, this is our answer. For lambda equals 1, our eigenvector is negative 1, 1. Now that we've found our eigenvector for 1, which was negative 1, 1, we're going to look at our second eigenvalue of 5. Now we're going to use the same exact method as we did for the previous eigenvalue. We're going to use our identity. Mr is equal to lambda r, with r being the column vector, lambda being the eigenvalue, and m being the original matrix. So, using the same method, we're going to subtract mr from both sides. We're going to grab 0 equals lambda r minus m times r. We're going to set r is equal to our unit matrix times r. Then we're going to plug that back in here. Lambda times the unit matrix times r minus the matrix times r. Now we're going to see that we could pull r from both sides, pull it out. Now we have 0 equals lambda times e minus the matrix multiplied by r. So, just like last time, we could substitute in lambda equals 5 for this lambda. We have our unit matrix, and we have our original matrix, which again was 3, 2, 2, 3. Now substituting these in, we get 0 is equal to 5 times the unit matrix minus the original matrix, 3, 2, 2, 3, times r, the column vector. Now, it's a little bit more complicated because we have 5 times this, which will then do the extra step to say that our new vector, our new matrix here is 5, 0, 0, 5, subtracted from the matrix 3, 2, 2, 3. And again, times the column vector r. Now that we have our equation here, we can simplify using matrix subtraction, which will then give us 5 minus 3, which is 2. Then 0 minus 2, which is negative 2. 0 minus 2, negative 2 again. 5 minus 3, 2. Again, multiplied by our column vector. Now, just like before, we can simplify this by row reduction. So we can have 2, negative 2 on top. Simplify the bottom parts out. Get 0, 0. Then we have a number here and the negative of the same number here. So with our same simplification methods, we can say that's 1, negative 1. And zeros on the bottom. Multiply it again by our column vector r. Now, just like before, we know that our column vector r is equal to xy, and we can simply plug that in. 0 is equal to x, y, multiplied by the matrix 1, negative 1, 0, and 0. And again, just like before, we multiply these two matrices together to get two equations, which then we will get x minus y equals 0 and 0x plus 0y equals 0. Just like last time, we don't care about that second one because that's just a true statement. But now we look at this top one and we have a relationship between our x's and y's. So we can simply say that x is equal to y in this case. Then going back to our vector xy, and we have a relationship xy, we can substitute x in for y. You see an x here, we plug in y. and is y on the top, y on the bottom, same exact thing. We can just set y equal to 1 and have our simple eigenvector of 1, 1. So to summarize, the lambda equals 5 value has the eigenvector associated with it to be 1, 1. This technique for finding our eigenvectors can be applied to any type of problem as long as you have your eigenvalues in the beginning. Thanks for watching.